I think you're muted. We can't hear.
Okay, sorry. I was saying hello, everyone. Good morning. Thank you for joining today. We have today Professor AbdulHai AlAlami, who is an associate professor at the Sustainable and Renewable Energy Engineering program at the University of Sharjah in UAE. His areas of expertise include solar energy and material removal, green building and insulating materials, solar steam turbines, and manufacturing and mechanical energy storage. Based on this, Professor AbdulHai will speak to us today from his experience on innovative energy storage technologies. So I'm leaving the floor for you, Professor, and you can start.
Thank you very much for the opportunity and for having me this morning. I hope that everything is clear. You can see my presentation and you can hear me well.
Yes.
Perfect. So thank you again. Today I would like to speak a little bit with you about energy storage, how it's important, and what is the state of the art currently. We will have to clear a little bit of misconceptions, but first let me tell you where I come from. I'm from the University of Sharjah, as you know, it's in the United Arab Emirates. And it's very close to Dubai, so a lot of you, of course, know where Dubai is. And it's one of the biggest universities in the country in terms of size and in terms also of like student body. And currently, we are doing a lot of like work in terms of research on so many different things, including, of course, energy, which is the department that I come from, the Sustainable and Renewable Energy Engineering Department. And of course, my main concern right now or area of interest is energy storage and not the conventional energy storage. So why is it important? Let me just ease you also without boring you into why energy storage is important. These are some of the statistics that we have. The energy consumption in the world, of course, what is the, after people started to discover many resources of energy, we started to use them, and sometimes we use them directly. The y-axis, of course, is terawatt hour, which is like an energy measure. And the progress of course, we went from traditional biomass into coal, into oil, which is the fuel, the fossil fuel. And then we started to look at other fuels, like, for example, gas, nuclear, and then the renewable resources as well. But of course, what is important in this graph isn't just the sources of different sources of energy, of course. It's the amount of energy that we are consuming and we continue to consume. Of course, there have been a very huge inflection point. So if you look at the scale here, like somewhere in the middle, I think this is where we have the 1990s or the 2000s. Although there has been an exponential growth, this exponential growth even became more, especially after the invention of the smartphone and the tablet. So the people who didn't even think of having a phone or having like an electrical device, now they have perhaps a phone and a tablet and maybe a laptop and maybe a desktop at work. So this is one of the reasons, or very simplistically, why the demand for electricity, because of course consumption is the demand for electricity, has increased and it continues to increase. And of course we need to face this with more production of energy. And of course this is where again the sources and where it goes. Again, we still rely on fossil fuels, which is the combined effect of coal, natural gas, and petroleum. And of course, also this goes into transportation, into heating and cooling, manufacturing, and also the generation, or the electricity generation in general. If you look at your house, this is where most of the energy goes. Of course, you're either heating or cooling. Of course, in cooler areas, heating is more important, but in hot areas, like for example, the United Arab Emirates, cooling is more important than heating because we have like heat almost all the time. And of course, you have to operate again your computer and your smart phones and tablets and all of that. So this is where everything is going. And in general, the way that we generate heat, I'm going to, of course, focus a little bit on what happens in the Middle East. We have different types of energy generation devices or ideas. One of them, of course, is to use, again, fossil fuels to have some rotary equipment or machinery. These can either be, like internal combustion engines. They can be gas turbines, like the one that I'm showing here, and I'm showing it here for a reason. You have steam turbines that uses external combustion that generates steam, of course, and then this steam goes into a steam turbine. The steam turbine rotates. It rotates a generator that gives us electricity. This steam turbine, of course, it has double, benefit. I can get, for example, water out of that, and also, of course, the idea of having external combustion means that if I can replace the combustion with a different source, I can still get the steam that rotates the steam turbine, and which also rotates the generator. So people started to invent solar and nuclear thermal power plants, where I use the temperature or the heat that is generated by a nuclear reaction to superheat water and get, of course, the steam into the power cycle, and then also get the water perhaps out of that, in order to prevent desalinated water for drinking or for irrigation or for whatever. And of course, when we look at, of course, the Middle East, we have like a big dilemma, and I think this is consistent in all of the countries, not only in the UAE. Most of the electrical load or the demand comes from air conditioning, and the electric load also is mostly supplied by gas turbines. The difference, or the big difference between gas turbines and steam turbines, is that in a gas turbine, it's of course very efficient and very strong, and it lasts for a very long period of time. We have a lot of heat output that is not used. For example, you can have an exhaust of, like 500 degrees Celsius or maybe more. And of course, you have the emissions, which is the CO2 and the nitrogen oxide and the sulfur oxide, all of these things that are very harmful for the environment. Whether you, of course, believe in global warming or not, these emissions, if they go directly into the environment, it's not going to be beneficial for the environment or for life. And again, why people use a gas turbine? And if you think about it, a gas turbine is actually just an engine, an aircraft engine that is repurposed in order to generate electricity instead of generating thrust. So it's a very important, of course, issue to collect that heat in what is called, or what is known as regenerative cycles, in order to perhaps heat some water, turn it also into steam, and we have a combined cycle. Because again, in the Middle East in general, and perhaps in the Gulf states in particular, the generated heat is not going to be beneficial. Even in winter, we don't really need that much heating. We need mostly air conditioning. So I'm just going to focus on Sharjah. This is, of course, a publicly available table or document or statistics from Sharjah Electricity and Water Authority. This is, of course, the power generated based on unit type, what they're using in order to generate this electricity. So we have steam turbines, we have gas turbines, and we have diesel. And also we have things that are coming from outside, and this is, of course, the summation of, outside in terms of federal grid, but this is, of course, the total that comes from all of this. And as you can see, if this is 121 million kilowatt hour, here we're talking about 1 trillion. So we're 1 billion. So here we have a big difference, and this difference, of course, can be seen here even more clearly. So the red line here is the gas turbine. So this is the installed capacity. The steam turbines are very close to, of course, the lower part of this figure, and diesel units, which also have a lot of issues in terms of emissions and maintenance and all of that. But the dominant or the most dominant supplier is the gas turbines. And of course, again, this as somebody who works in energy, and even if you if you don't work in energy, but you like working at high efficiency or being conservative, this is not really good, because these are very expensive to operate. Again, the emissions and the heat generated that is wasted, unless, of course, we have a regenerative cycle. And again, this is very typical, by the way. This doesn't only apply to Sharjah. This also applies to like any country in the world where you have, for example, this is, of course, the seasonal demand for example, with the winter months, especially in the Middle East again, and in Sharjah in particular, or the Emirates in particular, we have very low demand for electricity in the winter months, which is, for example, you can say we start in November and then goes all the way to February. As you can see, we have demand that is lower than a certain threshold. But once the summer starts, we see that, of course, this blue line is for the whole Emirate. This is Sharjah city, and these are the two main cities in the Emirate of Sharjah. So like these are, again, the demand is quite high during the summer months because most of the electricity generated has to go, to supply air conditioning most probably. Of course, this is again in table form. But this is, of course, not, you may or may not be, like interested in this. I hope that all of you went into sleep because I went into lecture mode. Now comes the real question. What is missing from, the report and from the statistics that we have seen? Like we have, many ways that we can generate electricity from, be it renewable or not renewable. We have, fossil fuels, we have gas, we have many resources, and of course, with the changes in the socio-political, situation in the whole world, we have all heard about the energy crisis that might actually hit sooner than we thought. So we really have to start to think about making use of all of the energy that we have to try to make sure that we're able to store it. Okay, so in the report, and this is just one quick example from a country that has a lot of energy resources, be it in terms of, for example, the fossil fuels. We have a lot of gas, we have a lot of petrol, we have a lot of sun, if you want to think about it in terms of renewable. So what is really missing from this report is actually the provision to store. Nobody talks about storage. Nobody talks about what about if, like all of a sudden, we have a certain situation that requires no access, for example, to external energy sources, and we have to rely on what we have stored. Are we ready or not? So this is again I'm just going to revisit this figure, and I'm just going to put a line here. This line over here. Oh, sorry, press too fast. The line over here, if you can see it, the black one. This is called the base load. So this is where, of course, like a certain country or a certain city or an emirate, they decide that this is the maximum, or not the maximum. This is the load that most of my instruments or most of my installed capacity or my energy generation equipment have to operate at. And of course, the higher we go with the base load, which means what I have to supply, for example, have two options. I either place it over here, which means that if I place it at the top side over here, I'm going to pay a lot. This means that instead of buying one gas turbine, I have to buy two or three. And these guys are very expensive to buy. And we really have to find budgets for them, and we really have to be able to install them and operate them and maintain them. So we're talking about a lot of money here. And what I mean by money, like an individual cannot buy them, maybe a big company cannot buy them. This has to come from like a big resource where the government maybe have to be involved in order to increase or decrease how much electricity or energy generating equipment are installed. So again, what happens if I put it over here? I'm going to pay a lot. I may or may not be able to afford all of this, but what usually happens is that we look at the base load, which is like a certain low or lower set point. And whenever I have that excess or the peak that exceeds this base load, I start to run the extra generators or extra pieces of equipment that would help me supply the load whenever I need it the most. But if you look at this figure, and this is where the two, like green triangles come in, this area over here where the base load is, because again, the base load I cannot change, and I would rather operate this all the time. This part over here is operating above the demand. Okay, I'm sure that all of you are able to notice the demand over here is much lower than what I'm producing. So what do? And again, I cannot, for example, like tune what I'm generating up and down, because I would rather work on something that is consistent. I don't want to overstress my system by starting it and then stopping it, starting it and then stopping it. It would be much easier and better for the life cycle of the equipment to operate at a certain constant load all the time. So the green areas over here are opportunities, you can call them for me, to store energy. And the beauty about this is that if you can see these two green areas, if you sum them up, they're much bigger than the area over here, or the total area where I need extra energy over my base load. So in fact, what I can do, I can actually decrease this or lower this line over here. And of course, the more I lower it, the more less budget I'm required to have. And in order to make sure that these two green areas are equal to that area over here. Okay, so this is like the philosophy behind having, of course, like an energy storage, solution in mind. What I want to ask you right now is, and maybe if you can help me answering it, I don't know. Like I'm keeping one eye at the chat. The energy storage. Whenever we say energy storage, what pops to your mind? What comes to your mind whenever somebody says storage or energy storage? The first thing, don't overthink it. Before we go to the next slide, Allah, battery. Most of the people, or actually two of the people, are saying battery. I'm just gonna wait 2 more seconds for somebody else to type.
Hello, yes?
Maybe. Yes.
Yeah, I can hear you.
Yeah, but I'm saying no. I'm just waiting for people to answer. So we have somebody who said hydraulic head. Okay. So we have 2 answers that says battery in the chat. I'm just keeping an eye on the chat. Okay, خلاص, let's close the thing. Maybe somebody has a sandwich in the hand and don't want to disturb that by typing on the keyboard. I understand. So batteries, 2 people said battery, 1 person said hydraulic head. I like, the third person, although I know none of them better. Why is that? Because batteries are not the only option, or they're not the only solution, in terms of energy storage. These are the energy storage technologies. I'm going to show you, of course, another image that have what we call the energy storage ecosystem. So the energy storage technologies, let me start from the right. Electrochemical storage, chemical storage, thermal storage, and mechanical storage. These are, we can say that these are like almost all of the energy storage technologies that are available. If you see here, the electrochemical storage includes batteries, like you mentioned, but batteries also, as you can see, is only one tiny fraction of the available technologies for energy storage. So batteries, of course, they include lead-acid batteries, the old ones. They include lithium-ion batteries that power the Tesla cars, for example. They also include flow batteries, the big batteries that are, for example, sodium nitride batteries, the NAS batteries. We have also capacitors and supercapacitors. These guys are also electrochemical systems because I have an active chemical material that is connected through an external circuit here, and then this what makes the electrochemical system operate. Of course, why are batteries this popular? Why, whenever we say storage, only one person says something else other than batteries? It's again, they're small, they're compact, they're easy to use, and they're also like available. That's another issue. What you need to do, or what we need to do whenever we think about energy and how to store energy, we need to also look at the source at which the energy is actually generated or converted. Because as I'm going to mention in a couple of seconds, converting energy from one form to the other always creates losses. Okay, so if, for example, I have a certain amount of electrical energy and I want to store them in batteries, some of this energy is going to be wasted, or it's going to be lost. Okay, chemical storage, of course, hydrogen storage these days is very important, and a lot of people are thinking of generating energy or electricity from hydrogen through, of course, hydrogen fuel cells. But as you know, one of the most important issues is actually storing this hydrogen that we're generating, because hydrogen is very light. If you don't store it, it might, even leave Earth because it's very light. It's the lightest element, as you know, or it's the lightest chemical element in the world. Of course, we have also thermal storage. We can do it through sensible heat storage, like in a heat exchanger, for example, or also we can do it through what is called latent heat storage, where I have a material that can change from one phase to the other. Like, for example, some wax can go from solid into liquid if I heat it, and then it would go back from liquid to solid. We also have the mechanical storage, methodologies or technologies like pumped hydro, and I think this is what our colleagues mentioned, the hydraulic head, which is of course called pumped hydro. I'm going to talk about it a little bit. We also have flywheels, and also we have compressed air energy storage, which I'm going to actually focus on a little bit extra today. As you know, or as you have heard, there's the renewable energy, or the National Renewable Energy Laboratory, or the NREL. The NREL usually, or the way that I know it, it actually keeps the efficiency chart, they call it, per year for photovoltaic cells, but they do more than that. So they have that efficiency chart, and also they have other very useful information. For example, this one over here is the ecosystem of energy storage systems, and they're classified for, the bulk system, or how much energy I can store, like for example, large scale or small scale, and here the average duration in terms of the charge and the discharge. So as you can tell from this figure, the higher to the right I can go, the better I'm going to be. Why is that? Because the higher to the right I go, first of all, I'm going to get like the bulk, or the large scale energy storage, you can call it. And also at the same time, I'm going to get the duration, or the maximum duration of charging and discharging at the same time. So not only am I able to store a lot of energy, I'm able to give and take that energy over a long period of time. As you can see here, we have the hydrogen is number one. And again, like I told you, the higher on the right you are, the better. We have also pumped hydro storage. I'm sure that you know what or how pumped hydro storage works. If not, we're gonna discuss it in a second. And also there's a compressed air energy storage, and all of that belongs to the green, like color, which is mechanical storage. Okay, so this is also a nice color coding of all of the storage technologies that are available. Batteries. The thing is that, whenever we say storage, we say batteries. It's in the middle. It's in the sweet middle region, where it's not too big and not too small. If I need something that is bigger, and why does it reach all the way there? Because if I need more storage or bulk storage, I can connect these batteries together, and they can have like a big battery bank, and they can use it to store a lot of energy at the same time. But there is like a limit to how much these batteries can give me back in terms of current, because you know what power is. It's current times voltage, and what energy is, it's current times voltage times time. Okay, so this is where the batteries, actually lack the things that pumped hydro storage or compressed air energy storage have. Of course, on the low side here, we have supercapacitors, and we have flywheels, and we have, of course, even superconductors. So these guys over here, they take and they give the energy very quickly. Sometimes I need that, and sometimes I don't. So whenever I need an instantaneous, charge or discharge, or need for energy, I use supercapacitors or flywheels. And also, like our colleague Hisham mentioned, that we can also use hybrids, and this is also very true. We can use any mix of the technologies that you can see in front of you. The most important thing is that I have to have, like a good control and good switching on and off, depending on the demand that I have. Okay. So I'm going to focus today, to be honest, I'm a mechanical engineer by training, so I'm going to focus a little bit on, the different options, the innovation, the things that are not batteries. Okay, so these are for large scale energy storage, like we mentioned. We can go pumped hydro. I'm going to talk about it a little bit. We can talk about, of course, steam storage. We can talk about big battery banks. And again, let me just go back to the slide. If you can see here, like the line that goes all the way to the right, like this is like all of the lines over here, they mean something. Like, for example, lead acid batteries cannot reach the bulk storage as much as the lithium-ion batteries. And since it's higher or on top of lead-acid batteries, which is the conventional, of course, batteries, this means that it can give us a faster charge and discharge cycle. So this is what we're looking for over here. So the main two technologies that I will be covering today are pumped hydro and also compressed air energy storage for large scale, of course, energy storage. That's number one. And number two, things that are not batteries. So I think, in my humble opinion, although batteries are going to remain to be important and they will remain to be with us, because you cannot, for example, if you want to charge your phone, you cannot have or build a pumped hydro storage station with a big dam and a lot of water next to your house or in your car. Okay, we'll still need batteries for certain applications, but at the same time, it's not going to be the win-all or the go-to solution all the time. So pumped hydro storage is, of course, the storing the energy. And I'm just going to use the schematic. I hope that you can see my mouse. Whenever I need, I have excess energy, or I'm charging. So this is the charging mode. I have two reservoirs or two, I know what a reservoir is, like two containers of water or fluid. Whenever I have excess energy, I pump it from the lower reservoir to the upper reservoir, okay, through a small pump. And this can take a long time because I have excess energy. Maybe people are asleep, they don't require energy. And whenever I need energy, we go to the drawing here on the left. Water starts or allow water to go into the water turbine that is connected to a generator. I get my electricity, and then the water goes back to the lower reservoir. So this is basically what pumped hydro storage is. This is different than hydropower. Hydropower in general, I have something that looks like this. I'm sure that most of you heard of or maybe visited Niagara Falls, where they have installed big water turbine. This is, of course, by the way, a person. And these are the turbine inlets and outlets, and you have the buckets over here. So this is where water goes in, and this is where water comes out. And then you have, of course, the rotation, and then you have the electric generators where you get your electricity. So this is hydropower in general, but strictly speaking, if I'm talking about storage, I am looking at pumped hydro storage, and I can do this anywhere, which means that I don't have to have a waterfall, I don't have to have a running river, but if I do, then I classify this as hydropower and not pumped hydro storage. And of course, the way that it works or the way that it operates, I have, this is like a typical cycle. This is a week, okay? This is the water level, if you can see it. And of course, the week starts on Monday and finishes on Friday. And as you can see, the water level is high during the start of the week. And these are the different cycles in terms of generation and pumping. So generation means that I'm giving or allowing the water to go from the upper reservoir into the lower reservoir through the water turbine that rotates the generator, and the generator rotates and give me electricity. Okay, the pumping part where I'm giving, the system energy, and this happens if you remember the curve that we just showed you. I have a central location where I need electricity, but while in other locations where people, for example, this is early morning, people have not woken up yet. This is late night when people have gone to sleep. Okay, so these are opportunities for me to actually do the pumping, which means that taking the water from the lower reservoir, the lower tank into the upper tank. And then whenever the day starts, I start to allow the water to go down and then turn the turbines and then give me electricity back. Okay, so this is the maximum storage. This is the water level, maximum water level. As you can see, sometimes I don't get the chance to fill through the week the upper tank as much as I want. So I reach Friday, which is the end of the week, and the reservoir have very little amount of storage. But the good news is during the weekend, I expect people to wake up late so that I have a chance to pump it all night, for example, and get the upper reservoir filled. So again, this is something that is very typical for a country that has lakes or some country that has a river. You use, the pumped hydro storage in order to do this. And of course, there are a lot of benefits in terms of, the control of the energy storage at a very big scale. And of course, a lot of the people, they call the pumped hydro storage dams as the big battery. So we still use the batteries to compare things, but again, you have a lot of energy in gigawatts here, and this might be enough to provide energy for the whole country for a very long period of time. So what if the country does not have enough, or does not have rivers? Sometimes you have a very mountainous area. So this is a very ambitious project that is taking place currently in Dubai, in the United Arab Emirates. It's very close, of course, Dubai to Sharjah. But this is, again, a very ambitious project because all of the rainwater that falls on this area, if you can see, it's a very mountainous area. And there is like a small lake that has already generated here due to that rainfall. And this almost stays all year long. So what happens here is that they're starting to build, like this is the lower reservoir over here. This picture is taken from the upper reservoir. They're starting to build a big tank that has the mountains on its back. So they're building something over here to retain the water. This area over here, I'm going to show you in the next slide. It has the electricity generation, and then water keeps going down until it meets with the lower reservoir. So this area over here is the bird's eye view of this area over there. Okay, and of course they're building the upper reservoir because the lower reservoir is already there, and they're expecting to have 250 megawatts, and this is of course like crazy. This is a large amount of electricity, per this station in particular, which is going to be also powered by solar energy, like the pumps that pumps water from the lower reservoir to the upper reservoir comes from the Mohammed bin Rashid solar park, if you have ever heard of it, which is one of the biggest projects I think in the world for PV production. Sometimes they have more energy than they need, so they route it to the Hatta. They call it the Hatta power or pumped hydro storage power plant, and they use, of course, the electricity that's generated from the PV, which is renewable, to pump the water into the upper reservoir, and then whenever you need energy or you are working in a peak conditions, then you can start to allow the water to go down, and then you have the generation. So this is the generation section. So water comes from the top here. It goes down. No, I think I'm mistaken. The water comes from here. Okay, so this is like the upper reservoir over here. Water goes into the gate over here. It goes down. It rotates the turbine in blue. Okay, and then it leaves, and you have the generators upwards, and this is where the electricity connectors that goes into the grid. The water goes in from here. I hope that you can see the mouse, which is to your, the right side. Okay, the right side. This is where water goes in. Of course, this is a surge valve, and then this goes into the turbine. The water turbine, of course, the water turbine design, by the way, has not changed in the past maybe 100 years. So this is just, what do you call it? Like a water mill that rotates, and then you extract the water or the water power, and then you allow the water to go back into the lower reservoir to be pumped, of course, back again, and then we get the electricity and we distribute this electricity. Okay. So this is one, solution or large-scale solution that is not a battery. The other one, and this is of course closer to my heart because like we're doing, I personally work on this, and like my team also works on this, which is compressed air energy storage. And here, air is compressed using the excess energy into large caverns. Of course, caverns means like a big, opening in the ground. And keep this in mind because I'm gonna explain why it's important to countries that have oil and gas and perhaps like water wells or salt wells. Okay, so this is where the potential energy is stored. So as big as I can get the compressors to be, that would be nice. So I can compress that air underground in a tank. And then, of course, whenever I need this energy back, I can release this air into air motors. Again, just like a windmill, but much smaller, much compact. So air is hitting the blades, and the blades are rotating. This is called an air motor. Some people call it a turbo expander. So this is the kinetic energy from the air into, of course, mechanical energy in this wheel. And then I connect this wheel to a generator again. So I have rotation from the wheel. The generator rotates, and then I get my electricity from that generator. Okay. Of course, one of the things As if you want to read on this, one of the, of course, the important things that I need to do is, of course, to thermally manage this. We're going to talk about that in a second. So why do we need to have thermal management? Of course, this is what I was just explaining. We have extra power. We operate a compressor. And as you know, the more I compress, the higher the temperature. So here I have to have a provision. I need to think about how I can get the heat outside of the air so that it would be stored underground or in a big tank. And then, of course, this is the charging part where I need to store the power. I have excess power. So if I stop needing the power, stop having the power, and I need to give the power back to the grid, I allow air to go into that turbine. Of course, here I need to give the heat back to the air. If you're thinking why, if you've ever used an aerosol, for example, air freshener, insect killer, for example, or deodorant, once you press on that button a little bit and you touch the nozzle, you feel that it's getting cold. So we don't want that air to be cold or too cold that it would start to condensate perhaps the vapor in the air into droplets of water. So this air turbine, because it has like blades, and these blades, I don't want these blades to hit anything other than a gas. So if they are like liquid, they would be damaged. So I don't want this damage to happen. So I give the heat back, and this heats the air to an appropriate temperature, and then the air goes back into exhaust while I'm rotating that generator, and they give the energy back to the grid. So this is, again, the basic idea. It's much different than pumped hydro storage, of course, because here I'm working with what is known as a compressible fluid. Of course, in water is not compressible. So I can apply, for example, Bernoulli's equation. I'm not sure if most of you are, interested in engineering, but again, Bernoulli is a very simple equation that gives me all of the powers that are affecting a certain fluid, be it weight, be it pressure, or even the velocity, that could be related to the velocity. I cannot apply those equations, but I can apply what is known as the isentropic relations that are derived from the ideal gas law. I'm not going to bore you too much with with math, but this slide in particular comes from NASA's website. I usually keep the NASA logo. So if you're interested, you can just look at the isentropic relations, and you can go into the NASA website. It has so many different slides for different courses, like you have some for heat transfer, for fluid. It's a very useful, very free also site. So you can actually go there and get all of the relationship that governs pressure and temperature. And of course, the type of fluid that you're using. In our case, we're using air. So the specific heat ratio, or gamma, for air is 1.4. Okay. So you can do the system design and get the most out of your compressed air system. We previously mentioned, of course, that the compressed air energy storage system are arranged by how I manage the heat. Okay, so if I don't care about the heat, where it goes and where it comes from, like I don't have any heat exchangers, they call it a diabetic system. Okay, and this is not derived from diabetes, which I have by incident. It's not the disease. Diabetic, not diabetic. Diabetic means no care for heat storage or heat management. While in adiabatic systems, I have either TES is the thermal energy storage. I have dedicated thermal energy storage, or I don't, but I still manage the heat. So if I have dedicated thermal storage, I call it TES, or with TES. Without TES is if I don't have dedicated heat exchangers for this purpose. Okay, isothermal compressed air energy systems are the latest, where they're still in experiment. The people are still experimenting with them, where I can do or increase the pressure very slowly in very small steps. They call it the pseudo equilibrium steps, in order not to raise the temperature or decrease the temperature very suddenly, so that I would get all of the thermal effects. Okay, so all of these are viable models that I can use, but you have to specify what you're doing with the heat. It's very important. Of course, again, I'm not going to, I promise not to bore you with math, but this is where it all comes from. This is the ideal gas law. We know it from physics. PV equals nRT. And of course, air does not behave as as an ideal gas. So I have to actually modify it a little bit and I need to go into the isentropic or the polytropic model, where for air this works very fine, where PV to the power n is a constant value. So I can calculate all of the pressures, all of the temperatures that I need, and of course I can also calculate the theoretical efficiency, which can be as big or as high as maybe 60 or 70%, depending on the pressure. The higher the pressure, of course, the lower the temperature. The higher the pressure, the lower the efficiency will be. And if you think, is anybody applying this in the world? The answer is yes. We have two operational plants in the world. One of them is in Huntorf, Germany, and the other one is in Alabama, I think, the Macintosh Power South installation. So this is the Power South compressed air energy storage, and this is the Huntorf one. As you can see, we have the compressors, you have the big storage, and I'm going to talk a little bit about storage in a second after I explain this schematic. So you have two compressors. Whenever, of course, I have excess energy, I have a motor here, and this motor rotates the compressors, and the compressors, they fill this underground tank. As you can see, I have coolers, and these coolers, or intercoolers, sometimes they call them, sometimes we use them even in cars. They store the heat for me, so I can give the air the heat as it decompresses. So this is the charging cycle where the air storage underground gets pressurized. Once I need the energy, I stop the motor. Now it turns into a generator. So the air, I allow the air to go into the expansion turbine, and these guys start to rotate, rotating a generator, and then I get my electricity back. What's special about the Huntorf installation is that they have combustion. So I have instead, of course, of going to the turbines as air, I have fuel. I ignite the fuel, and then I start the expansion, and I get much more electricity back. But of course, as you know, here I have emissions, I have heat that I have to work with. So again, like, this is not as renewable as you want it to be, but at the same time, this would definitely satisfy the demand for electricity without having to buy a gas turbine, because I already have the compression in the air storage. And of course, this air storage, it can either be a tank, but again, in the case of the Power Macintosh power installation, they have a salt mine. What does a salt mine mean? It means that, you know, it can be a water well, it can be a gas well. And why are these important? It's because they're already impermeable. Okay, I'm sure that you know what I mean. Like, for example, if you have a well that has water in it or gas in it, it's like a big balloon, and this balloon is already, you know, like does not allow the gas or the water to escape. So I can actually save that air and pressurize it, because I don't want it to be, you know, leaking. If it's leaking, then I'm not going to get any pressure done. So if it's not leaking, if it's a well, then I'll be able to pressurize it. Okay. I have a question. Do we need to heat up the gas before the turbine? The answer is yes. Okay. So because otherwise you're going to get to very low temperatures, and again, if you have moisture in the air, you're going to get condensation, and this condensation is going to turn that vapor into liquid droplets. And as the turbine is rotating, it's going to start to hit these droplets, and you'll damage your hardware. And you don't want this to happen. So thermal management, again, is very important. So what we did in the research, we did two things. First of all, since we don't have, or not always do we have big caverns or underground tanks, we looked at something that is modular, something that is very similar to the batteries, or having a battery bank. And what this means is that instead of having like one huge tank, we have smaller tanks, as you can see here. And this, of course, for the sake of experiments, we're going to show you what we also have done shortly. So we have a gas source. We experimented with air and with carbon dioxide as well. So you fill these tanks, and then you connect them with automatic, what they call it, solenoids. And these solenoids, of course, they open and close according to our will or our programming, and then this goes into the air turbine, and then we get the electricity generated. And again, we can operate this either sequentially, or we can operate it in, you know, like together. Like if we open the three solenoids, we're going to have a lot of power and we're going to rotate the air turbine, for a long time. While if we do it one by one, if I don't need a lot of energy in a very short period of time, then I can allow each of these cylinders to decompress, and one by one this would happen. So this is, of course, the tandem operation, all of them at the same time, and we operate it, as you can see, at very low pressure, just to test how much we can benefit from the system. So you have 3 bars, 2 bars, and 2.5 bars and 2 bars. This is the tandem operation, and this is the sequential operation where I try to prolong, the operation of the system as much as I can. And of course, if you imagine what we can do, we can have as many tanks as you want. You can have like 1,000 tanks, and these 1,000 tanks aren't going to be that big. Which schematic? This one? How it operates? Okay, so how it operates, we have 3 cylinders, and these 3 cylinders, they are under pressure. So whenever you have extra energy, you have a compressor, and that compresses air inside, or like any gas that you're using inside of these tanks, so you can get them to as high a pressure as possible as you need. And then you can connect them with solenoids, which means that valves that you can open and close using a computer. So you can either operate all of them, which means that I'm going to open all of these valves at the same time, or I can, of course, this gives me a lot of power, but the cylinders are going to be depleted in a short period of time. Or I can allow the only one of them, this is open and these 2 are closed. So I'm getting, air decompressing from only one cylinder, and the turbine is rotating. Once this depletes, this closes, and then this opens. And then this is what we mean by sequential operation. And this is, of course, the voltage that we're getting from all of the 3 operating at the same time at different pressures. And this is what we get from each of the tanks discharging at the same time. And again, yeah, before I leave you, because I don't have that much time left, what we can do, we can have as many tanks as you want, because these tanks are very small. And just let me show you very quickly. I'm just gonna go into like one last slide, and then I'm gonna stop here. This is, according to our latest experiment, this is the size of a battery. If you can see the dent down here, the green part over here is the amount of energy or the amount of space at 40 bars of air pressure that is equivalent to the operation of one battery. So this is not as huge as you think, because if you think about it, this is the yellow part over here, or maybe here I can explain it a little bit better. This is also to scale. These are solar panels that are going to give me the same power as that tiny little square over here, which is a petrol engine that gives me the same power. So instead of using all of this like square over here, I can use this tiny little engine. But if I want to have a sustainable and renewable source, like for example solar panels, then I have to really find the space for this. Okay, so if you tell me that maybe a small battery that is this big is going to replace what I'm proposing, which is like a big space to store air in, I can tell you, I can refer you to the previous drawing, and I can tell you, if there is a will, there is a way. If you want to go renewable, or if you want to think outside of the box, then you have to, of course, pay the price. So again, I'm not going to take any longer of your time. I'm going to stop here as dictated by our host. So thank you very much for being here today, and thank you for listening. Let me also, also before I leave, this is how you can actually contact me if you want to continue with this discussion. This is my email. I have also, published a book on mechanical energy storage. So if you like, you can look it up. You can Google it. It's Mechanical Energy Storage for Renewable and Sustainable Energy Resources. And let me know what you think about it and about this presentation. I'll be more than happy to take this, conversation further, inshallah. Thank you very much.
Thank you, Professor, and thank you for your time. If any one of you have any questions, you can just write them in the chat, and we will forward them to the professor, and we will send them to you once he answers. Thanks a lot again, Professor.
Thank you. Thank you very much. Thank you.